All right, recording is rolling. So welcome to Monday, April 17. I've got an FRQ lined up for you guys, rotational dynamics. Do that here in a minute. You guys know tomorrow's the quiz. Let's just do open notes like we've been doing. You guys know, of course, on the actual AP exam, you're allowed to use this page. So if you can get to the practice of just referencing this, kids got so excited too, right? They'll provide that to you. But yeah, but if you've been taking good notes, then I can help you out too. All right, so I've got this warm-up question for you guys before we do this FRQ. Okay. Before we go into that, anybody got any questions so far? That's right. All right, let's take a look at this warm-up question. All right, so I got this baseball. It's going to slam into this rod that has this pivot point right here. You guys see this pivot? Right? I've got a before and after. Right? So here's before, baseball going shoo. Right? And then after, boing, right? Baseball comes to a dead stop and the pivot starts rotating at some angular velocity, right? True? Right. Now, if it's horizontal, then it'd be constant angular velocity. If it's vertical, maybe that would be an initial angular velocity, right? But all right, let's call it omega, right? Okay. You guys get the premise? All right. Right. So this looks like some I might call this an elastic collision. I don't know. Maybe you have to run the kinetic energy before and after to see if that's really good. Right. But it's definitely not perfectly inelastic, right? It doesn't stick, right? It boing kind of bounces off, right? Comes to a stop. Okay, so there's some collision going on. I told you the mass of the baseball, right? That's the mass of the baseball. I told you the speed of the baseball coming in, right? It's coming in straight, horizontal. Right? I told you the location from the pivot point that it strikes. Okay? And I also told you the rotational inertia of the rod. Okay? There's enough information there where you can figure out how fast is that rod set into motion. Okay? So yeah, go ahead and take a minute and solve that. Right? Oh, and then the blank paper on your desk. I'm eventually going to have you guys do the FRQ on that. I mean, so. I'm going to pause this recording and give you guys a minute here. All right, recording is resumed. Let me see, show of hands, what you guys think. Okay. So how many guys got A? How many guys got B? How many guys got C? And who says D? D. All right, 1, 2, 3, 4, 5, 6, 7, 8. Okay, looks like about 7 or 8 of you guys got the correct answer, D. All right. So what was the setup for that? Like what's the principle? Conservation of angular momentum, right? You guys remember this one right here? Conservation of angular momentum, right? I mean, there's something rotational going on. There's some kind of collision going on. Maybe those would be hints that would have to fall into that category, right? Okay. So the sum of angular momentum initial equals the sum of angular momentum final. Okay. So you can say something like that. Now, one version of angular momentum is I times omega. Oh, and I gave you I of the rod, and I asked for omega, so that's got to be somewhere in the setup, right? Okay. In fact, that is the after situation, isn't it? Right? Because after the collision, right, the only thing that's moving is the rod itself, which is rotating, right? So I can say this is I of the rod times omega final, which you guys are solving for. Okay? But then where did all that angular momentum come from? Right? Linear momentum. Yeah, linear momentum. True, true. Right? It did start off as linear momentum, right? Now, how do you take linear momentum and put it in terms of angular momentum? MVR. Boom, 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 boom. MVR. Yeah. You guys remember this right here? MVR, right? You guys have seen this slide many times, right? So there's your MVR. Right? Right? So mass times velocity is just linear momentum. If you multiply by the radial distance from the pivot point, boom, you got angular momentum. Right? So here's where it came from. Here's where it went to. Right? So as an expression in terms of variables, I can say that the angular velocity is the angular momentum provided by the baseball divided by the rotational inertia of the rod. Okay, so let's plug in some numbers. I told you the mass of the baseball is 0.145 kilograms. It was going at 22 meters per second. It was at 1.5 meters from the pivot point, and the rotational inertia of the rod was 0.60 kilogram meters squared. Let's see exactly what the calculator says. 0.145 times 22 times 1.5 over 0.6. Okay, that is 7.975. And what unit would that be? Radians per second. Yeah, good call. Radians per second. All right, see that? All right, which to two significant figures would round to 8 radians per second. Right? Yeah, Leonard?
Derive MVR.
I've never seen them asked to derive that. I think you're just allowed to know that. Yeah, although I don't think that's actually on AP's equations though. So yeah, true. That's a good point to bring up. This MVR, know that one, have it in your back pocket. It's not on the AP the provided equations, so you just have to memorize that. Okay. You guys see that? Okay. Any questions about this one? All right. If I asked a similar question on the quiz tomorrow, you guys be able to handle that? Okay. Maybe not exactly that. Might have a okay, but pretty close to that. All right. All right. So let me pull out a rotational dynamics FRQ. Switch gears here.